Let's go over simple harmonic motion questions. We'll go through 7 questions in this video. Let's look at the first question. A pendulum takes 3 seconds to complete one full oscillation. What is the length of the pendulum in meters? The time taken for one oscillation is 3 seconds, so the time period with the symbol uppercase T is 3 seconds. We want to find the length of the pendulum, so L equals question mark in meters. A pendulum undergoes simple harmonic motion, so we can use this equation. Time period equals 2 pi times the square root of length over gravitational acceleration. We need to rearrange for L. To do that, we divide both sides by 2 pi, then we square both sides, then multiply both sides by g. This gives us L equals g times the square of t over 2 pi. For PHSI191, the value of g is 10 meters per second squared. Let's substitute our values. L equals 10 times 3 over 2 pi squared. To put this into the calculator, enter 10, then open parentheses, fraction button, then 3, then arrow down, then 2, then press shift, then the 10 to the power of x button to enter pi. Arrow right, then close parentheses. Press the x squared button. This should give you an answer of 2.279, which we can round to 2.3 meters. Question 2. A spring is hanging vertically and a 2 kilogram weight is attached to the end, causing the spring to become 30 centimeters longer. What is the spring constant in newtons per meter? We can use the spring constant equation here, where F equals negative kx. K is the spring constant, which gives us an idea of how strong the spring is. X is the displacement of the spring away from its equilibrium point. The negative is there because the direction of the force exerted by the spring will always be in the opposite direction to the displacement, i.e. the spring wants to return to its equilibrium position. We call this the restoring force. Mass is 2 kilograms, and we can calculate the weight force exerted by the mass. Weight force equals mass times gravity. So 2 times 10 is equal to 20 newtons. This weight force will be directed downwards, but the spring will exert an equal and opposite force to the weight force. The force exerted by the spring will have a negative value because it will be in the opposite direction to the displacement. So F equals negative 20. The displacement of the spring is 30 centimeters. We need to convert this into meters. To do this, we multiply by 10 to the power of negative 2 to replace the center prefix. This turns it into 0.3 meters. We want to find k, so we'll rearrange the equation for k. Multiply both sides by negative 1 to move the negative sign to the other side. Remember that a negative number multiplied by a negative number becomes a positive number. So negative f equals kx. Next, divide both sides by x, and we have k equals negative f over x. If we substitute our numbers, then k equals negative 20 divided by 0.3. Since the two negatives cancel out, we can just enter 20 divided by 0.3 into the calculator, which gives us 0.6 newtons per meter. Question 3. A 20-gram ball at the end of a spring is oscillating up and down in simple harmonic motion with a frequency of 2.5 Hz. What is the spring constant in newtons per meter? The mass of the ball is 20 grams. We need to convert this into kilograms. So we'll add the kilo prefix by dividing by 10 to the power of 3. This turns it into 0.02 kilograms. The frequency is given the symbol lowercase f and is equal to 2.5 Hz. 1 Hz is 1 oscillation per second. We want to find the spring constant, so we can use this equation. Time period equals 2 pi times square root of m over k. We can calculate the time period because time period equals 1 over frequency. So t equals 1 divided by 2.5, which is 0.4 seconds. We need to rearrange the equation for k. So k equals m over t over 2 pi squared. Let's substitute the numbers. K equals 0.02 over 0.4 over 2 pi squared. To put this into the calculator, use the fraction button, then 0.02, arrow down, then open parentheses, press the fraction button again, and enter 0.4, arrow down, and press 2, and shift then the 10 to the power of x button to enter pi. Arrow right, close parentheses, and hit the x squared button. This should give you an answer of 4.9348, which rounds to 4.9. Question 4. A pendulum is swinging with a frequency of 0.6 Hz. What is the length of the pendulum in meters? The frequency is 0.6 Hz, so we can calculate the time period t. T equals 1 over f. 1 divided by 0.6 is 1.6667 seconds, rounded to 5 significant figures. Using the equation we used in the first problem, L equals g times t over 2 pi squared. If we substitute the numbers, then L equals 10 times 1.6667 over 2 pi squared. If we put this into the calculator, then we get an answer of 0.70 meters. Question 5. A decoration with a mass of 1.2 kilograms is hung onto a spring with a spring constant of 260 newtons per meter. How much will the spring lengthen in meters? Mass equals 1.2 kilograms. The weight force exerted by this mass is 1.2 times 10. So weight force equals 12 newtons. The force exerted by the spring will be equal and opposite to the weight force of the mass. So F equals negative 12 newtons. The spring constant K is 260 newtons per meter. We want to find the displacement of the spring, which is the symbol X. So X equals question mark in meters. The equation we can use is F equals negative Kx. We want to rearrange for X, so divide both sides by minus K. X equals F over minus K. X equals negative 12 over negative 260. If we put this into the calculator, we get an answer of 0.046 meters. Question 6. If a pendulum has a length of 35 centimeters, then what is the period in seconds? The length is equal to 35 centimeters. We need to convert this into meters, so we multiply by 10 to the power of negative 2. This gives us 0.35 meters. We can use the simple harmonic motion pendulum equation. T equals 2 pi times the square root of L over G. Let's substitute our values into the equation. T equals 2 pi times square root of 0.35 over 10. If we put this into the calculator, then we get 1.175, which rounds to 1.2 seconds. Question 7. Choose the incorrect statement. Let's look at the statements. Option A. The force applied by a spring on an object is proportional to its distance from the equilibrium position. The equation F equals negative Kx shows that the force is proportional to x, which is the displacement of the spring. So, if the displacement doubles, the force will also double. Therefore, option A is correct. Option B. The potential energy stored in a spring is proportional to the amplitude. We haven't used this equation yet, but I show you how to use it in the Advanced Simple Harmonic Motion section. The potential energy stored in a spring, or E spring, equals half Ka squared, where A stands for amplitude. This is the maximum displacement of the spring. So we can see that the potential energy is proportional to the amplitude squared. If amplitude doubles, then potential energy would quadruple. Therefore, option B is incorrect and is the answer for this question. Let's continue to evaluate the other statements. Option C, a pendulum's period is not affected by its mass. The pendulum's simple harmonic equation is T equals 2 pi times the square root of L over G. You can see that mass is not included in the equation. Therefore, option C is correct. Option D, during simple harmonic motion, the maximum velocity is at the equilibrium position. If you think of a pendulum undergoing simple harmonic motion, then the velocity will be maximum when displacement is zero, aka at the equilibrium position. So option D is correct. Option E, during simple harmonic motion, acceleration is zero at the equilibrium position. The equation F equals negative kx shows us that if displacement x is zero, then force will also be zero. If there is no net force, then there can be no acceleration, and therefore, at the equilibrium point, acceleration will be zero. So option E is correct. That's it for the essential simple harmonic motion questions. Check out the A+ course if you want to find the advanced simple harmonic questions. In the next video, I'll go through waves, the final topic in the mechanics module.